institute. Anyway, I'm going to talk about neutral hydrogen as a cosmological probe, which is my primary area of investigation, and mainly my expertise lies in the Lyman alpha forest and in modeling the Lyman alpha forest to do, let's call it to address fundamental physical questions. However, I will try to complement this view with the mission by 21 centimeter intensity mapping and see whether also we can, let's say, consider these two observables in the same framework and what are the questions we can address by looking at these two observational probes jointly. So let me first start with this. So this is the amount of neutral hydrogen as a function of redshift, then the contribution to the energy density. This is multiplied by 10 to the 3, so it's a small amount, but nevertheless comparable to the amount of energy density of neutrinos and stars, which are supposed to be tracer of the large-scale structure, okay? People are usually focused on the amount of stars, which, of course, for obvious reason, they do shine, so we trace galaxies by looking at the stars in them. But here, omega H1 is about of the same order, and so it's intriguing to look at this quantity and see whether we can use this as a tracer. And so here, if I plot the evolution of omega H1 as a function of redshift, these points here are purely observations, right? Observation. Here you have them mainly from galaxy emission slide, but most of these data points here have been obtained by looking at damped Lyman alpha systems. So looking at the properties in absorption by looking at the spectra of either GRBs or typically quasars. And so most of the theoretical models, they might fit these data points. You see, if you look at them, you can maybe draw a line, like flat line, which would be a reasonable good fit at least up to, let's say, point something in redshift, or you can claim a mild evolution like this. And it's surprisingly stable, you know, over cosmic time in a period of time in which most of the physical quantities we are most familiar with, like the star formation rate, the thermal state of the intergalactic medium, the UV background amplitude, change dramatically, I would say, or significantly. So this stays remarkably stable over this huge amount of cosmic time. And I would also like to stress that most of the, let's say, semi-analytical models of galaxy formation that are very popular, they are tailored to match these values here at low redshift, and they fall short at high redshift. So it's typically you address this large redshift, high redshift observations by having dedicated investigations of damped Lyman alpha systems simulations with hydrodynamical simulation, which might or might not include radiative transfer and sophisticated physics. Anyway, it's a tracer, okay, and we do probe this energy distribution with redshift over cosmic time. However, so we might want to look, if we want to do structure formation, we might want to look at the perturbation, right? We want to look at the dynamical growth of structure, and the Lyman alpha forest is the main manifestation of the intergalactic medium, and so what you typically have is a bright source, which can be a quasar or GLBs, but most typically a quasar, and the quasar emits photons. The photons, they travel throughout the universe, and whenever in their intervening journey, okay, they encounter some neutral hydrogen, there is a scattering process is going on, and the electron, which is orbiting 1s, it will go to 2p, and eventually the electron will go back to the ground state and will re-emit a photon in a different direction, typically. So people talk about absorption, but in reality it's an atomic scattering process, which is very well known, and it has been known since many, many years, of course. And so the idea is that if you zoom in, you see all these, different environments, and where you are more absorbed, it means that there's going to be more neutral hydrogen along the line of sight, and when there are also narrow lines like this one here, for example, which might be connected to somewhat less dense environment. So my research in the last 10 years or so has been focused on analyzing, this line of sight in a statistical way to extract mainly the flux power spectrum. And you can do these things in 1D, of course, but the new thing that emerged, I would say something like 6 years ago, thanks to the BOSS collaboration, was also that you can also cross-correlate this information in 3D. So if, for example, you can cross-correlate the value of the transmission, it means the neutral hydrogen content along this line of sight, this pixel with this pixel here, with this pixel here, with this pixel here, and so forth, so on. Why is this important? Well, first of all, you will be probing larger volumes by doing so. Second of all, by doing these cross correlations, you are less prone to one of the most important nuisances, which is the continuum of the quasar, right? The continuum of the quasar, which is this long wavelength modulation of the Earth spectrum, which is connected to the source and has nothing to do with the intervening matter that you want to reconstruct, the intervening cosmic web. And so by doing this, you get rid of this long wavelength fluctuation. I think one of the first ones to point it out was Martin White, who is here. And you can address questions like, I can recover the baryonic acoustic oscillation, you can do geometrical studies. So it's a 1D observable, but it's also 3D, and this is really interesting and relatively new thing, and it has been used to do cosmological constraints. So, however, I'm not going to talk about cosmological constraints in terms of geometry. I will take mainly dynamical growth of structure. And the statistical properties of the Lyman alpha forest flux are being used to put tight constraints on the property of dark matter, including some dark matter candidates like the stellar neutrinos, ultralight boson dark matter, which is so-called fuzzy dark matter, which is very popular at this moment, especially in the US. And let me anticipate the results. The results are the following, that sometimes you invoke some properties of dark matter, which tend to erase structure below a given scale. Okay? Below a given scale, the structure, there is no power, and these lines will be, let's say, smoothed out. There are no perturbations. And there are some people that think that cold dark matter has problems at small scales, and they invoke masses, let's say, or values for these parameters that could kind of reconcile or ease these tensions. And typically, the values that they claim are in contrast with the Lyman alpha forest. The Lyman alpha forest would like to have structures down to the smallest scales, and would like to have substructure, let's say, and so typically these values that the Lyman alpha forest gives are in contrast with those suggested by people that aim at solving the cold dark matter problem of crisis at small scales. So this was absorption. Let's go to intensity mapping. So intensity mapping is very easy to build up a linear theory model of the 21 centimeter intensity mapping signal. And here you can write it in one line, and it's not very important, but the important thing is just the quantities that enter here are very easy to identify. Okay? And most important, there are two quantities that are relevant here. One is this mass function that can enter in this, the mass function, the abundances of dark matter halos in the universe, as given, for example, by pressure sector or embodied simulation of Tinker mass function, that will specify the shock noise level, the bias of the H1, and then most importantly, this relationship between the mass of the halo, dark matter halo, and the content of H1 that each halo hosts. This is one very important quantity. There is a minimum mass below which you don't have H1. This is for physical reason. Maybe the H1 is destroyed by UV background, and then there is an exponential. Cutoff at small scales, and then there is a power. Okay? So this empirical relation is also derived from simulations like this one investigated by Paco and co-workers here, Shai, Genel, and other people in this room. They analyzed the illustrated simulation, and they have very nice pictures like this one here, in which you can zoom in, you can follow the neutral hydrogen, the gas, and down to the smallest scales, and basically you see whether if you embed this relationship that you get out from this simulation into this formula here, you can get predictions for how this signal would look like in the post-ionization era. And it's pretty clear that this 21 centimeter power spectrum in redshift space would trace up to the bias, up to the brightness temperature, the underlying matter power spectrum. So it's clear to some extent. We will test this, and people have been tested this. But what I want to bring to your attention is that you have here the complementary information. One side absorption, you probe the universe, the H1 content in the universe by volume. Okay, the random line of sight are random, and so the universe will select them for you, and you will probe most of the volume. But this is an emission process in which you will probe in the H1 by mass. And so it's pretty clear that the two are connected to each other, and they provide complementary information on the distribution of H1 in the universe. So the degeneracy between the bias of H1 and omega H1 can be broken by using other probes. The progress has been made mainly in the modeling determining the values of H1 bias. This has been determined observationally, right, which is a pretty low value. And in study of cross-correlation, we do have also observations of the intensity mapping at low redshift by cross-correlating with galaxies. But the important thing to remember is if you want to predict the intensity mapping signal, you need to specify this relationship here, which will have a scatter, and the scatter is likely to be physical scatter, as it always happens in galaxy formation process. The scatter that you have is going to be physical, and is an important ingredient in the model. So if you put these two together, you can have nice plots like this one. This we made already 6 years ago with Paco, but basically it's the column density distribution function. You simply look at the H1 systems along your line of sight in the simulations, and you confront it with observations. So here you have, what I would like you to notice is the following, that you have a huge amount of dynamical range. You go from systems that are 10 to the 12 or 10 to the 13 or so, up to the system of 10 to the 22. So you really probably feel the cosmic web in the filaments, which is most of the volume. So that's why the number of this is much higher than this one, which will have a small volume filling factor, but nevertheless will contain most of the neutral hydrogen. Okay? So it's a very comprehensive view. And there is a good match for the Lyman alpha forest properties, relatively good match also for Doppler analysis. And here the things do not work. We know the reason. Physics gets complicated. Maybe there is cooling processes that we do not follow. But getting plots like this one is relatively straightforward, and it is telling you that probably the physics is kind of, correct, or at least is kind of, constrained by and at some level, right? And so here is a huge dynamical range, and it's very, very important that we have this right. So some key questions that I think are some of them I don't have the answer, of course. So the first one, is there a consistent model of the H1 evolution from high redshift to low redshift, from, let's say, after recombination? And what are the observables that we cannot fit? Because I believe that in this business you learn much more from the things that you don't fit, rather than if you look at the things that you do fit. To what extent H1 traces the underlying structure formation process, of course. And for example, in the intensity mapping, people have talked about scale-dependent bias, whether you can build up an H1 halo model that goes to very small scales, whether the shot noise level is so large that it can totally destroy your cosmological signal. And also, to what extent H1 evolution is influenced by galaxy formation, or for those of you that are interested in galaxy formation, there are many people, of course, whether you can use this data to constrain feedback models, right? You can, in 10 years or 20 years ago, there were people that were having models of the Lyman alpha forest totally produced by galactic winds, right? You have shells of cold gas going out in the galactic medium, and they were claiming that this could have been produced, this could have produced the Lyman alpha forest properties. In that case, it's pretty clear that we cannot use the Lyman alpha forest to do cosmology. And then the question, being a cosmologist, now one of the most compelling questions is there evidence of physics beyond lambda CDM? And to some extent, this could be neutrino masses, even though it's pretty standard physics, but we do want to measure this. To some extent, whether we can extend, since this is an high redshift probe, whether we can say something about the geometry of the universe by looking at this high redshift data. And of course, the thing that I'm most interested in is the dark matter nature, and to look at the dark matter nature. So I believe that for such an audience is pretty important also to outline what are the theoretical tools to address these two different processes. And let me briefly go through. For absorption, you use hydrodynamical simulation. You want to get down to masses of 10 to the 4 m-sun in gas. Dark matter only simulation will not work, unfortunately, or will be approximated at the level of 10–15%. For emission, dark matter only is good. Okay, it's enough. You don't want to go to very small scales. You can compromise a bit because you know that the halos that are hosting H1 will be, let's say, 10 to the 9, and so you want to resolve it at least with, I don't know, hundreds of particles, so you don't need such high resolution. So this is mandatory, and also because you want to fit at one time the 1D and 3D flux power, so you would like to have a self-consistent model, which is not present, okay, at this moment. High resolution needed, of course, like the one of Illustris, are needed mainly to calibrate dark matter models. Okay, if you have a set of hydrodynamical simulations with refined physics, you can use them and fold it into a larger box, and maybe poorer resolution dark matter only simulation to predict, let's say, to span faster the parameter space. Semi-analytical models have also been used up to, I would say, 10 years ago, and they're perfectly fine up to 10% agreement. There is also an halo model developed to study absorption by Hirsich and McQueen, which is interesting. H-halo models in this case are instead quite used by the community, right? There is lots of people working on this. Typically, to do, let's say, to have neutrino mass constraints or dark matter constraints, what do? You aim at fitting the one-dimensional flux power with a set of 20 parameters, which are nuisance, astrophysics, and cosmology, and you explore the parameter space by doing MCMC, so in a Bayesian framework, not frequentist, and in order to explore this parameter space, you need to build up a likelihood, which is based on order 10 accurate hydrodynamical simulations, right? In this case, the forecast, we don't have real data at this very moment, or very sparse or upper limits. The forecast made using mainly Fisher matrix, okay? So and it's obvious the reason you don't need this level of sophistication. And I believe a very promising avenue would be to cross-correlate, right, the intensity mapping with other probes to get higher significance of the signal. So let's talk about absorption, and this.
Sorry, Matteo.
Yes.
So why 10 to the 4 for absorption? I mean, this is the Jeans length?
Exactly. You want the Jeans length is a bit larger. You want to resolve it properly, right? Or you want to go down to the filtering length, which is, I will talk about this later. So you want to and these lines, these is also, under dense regions. So you want to have resolution. So this is a praise simulation, is I believe one of the most, let's say, highest resolution simulation. Jamie Bolton and Ewald Puchman have been working with them in the last few years. And so this is 40 megaparsec to under 2048 cube simulations. And here we are not interested, of course, in modeling galaxy formation. We are interested in getting numerical convergence with an SPH code in the Arnold-Ders region. We are interested in getting these filaments right? We're interested in checking primarily this. Of course, we do have to specify galaxy formation. We do have to specify and marginalize over thermal histories. And that's why we have one very big simulation, and then we have fewer other simulations to explore the physics. So what are the ingredients? So this is the gas distribution, but the ingredients that build up our observables are somewhat different, and it's, you can follow the evolution of these quantities here. This is the density, this is the temperature. The universe is cold. At some point it will shine because the ionization is happening, going up to 20,000 Kelvin. And then, this is the H1 fraction, and this is the peculiar velocity field of the gas projected in a plane of thickness. I don't recall at the moment. It's not very important. But the point that I want to make is the following, that our final observable is the flux. The flux is e to the minus the optical depth. The optical depth is a power law relationship, with the density field. Of course, this is simplification. It's called the Flack-Ratings-Gap-Peters approximation. Things are nonlinear. Peculiar velocities, of course, are important. And you need to specify all these ingredients to get the prediction of your flux power. So it's pretty important to have all these ingredients properly modeled in your simulations. Under the data point of view, I believe that we've been pretty lucky in the sense there are many people working on this, and we have three sets of data sets that are used. We have the low resolution, low signal to noise, BOS, SDSS3, now it's going to be eBOS, there's going to be DESI, actually DESI already started, and you have many of these, right? With DESI will go up to 1 million. So here, really, the statistical error bars are tiny once you extract the flux power spectrum. Then you have a set of medium resolution spectra, about 100, but at high redshift, and high redshift is very important. And then we have a set of, let's say, hundreds of very high resolution spectra. And you can clearly see by eye, this is not the same line of sight, of course, but you can see by eye that here you resolve the line, really the structure of the line down to the smaller scales, while here you don't. And so the questions that you can ask depend on the data set that you're using. In this case, you will need a lot of statistics to get down to the neutrino mass. This is the upper limit that you get, or to measure the baryonic acoustic oscillations. In this case, having medium resolution allows you to go down to smaller scales, right? Because high resolution means small scales. And then you can measure the thermal cutoff. You can measure the thermal property of intergalactic medium. And these, of course, spectra are very important for galaxy formation. There was also your talk this morning about the CGM properties or fine structure constant and things like this. Most of the data are publicly available, so people can use them. Of course, you need to get rid of the systematics, but it's a very interesting area of research. So one interesting question is the following. You take the spectra, high resolution, okay, and you have your flux power spectrum as a function of wave number. Look at the units, are second over kilometer, large scales, small scale. This is velocity space. Usually you tend to see these things in h over megaparsec. No, in this case you see this. These are data points, and the lines and the shaded area are simulations, like the one that I showed before. And this is the typical shape that you get. You have this large scale power, and then you have a cutoff. So what is producing the cutoff? There are several scales, several physical scales that enter in shaping the position of the cutoff and in determining the shape, the steepness of this cutoff. What is highlighted here is two particular effects. And if you take the ratio with the lambda Coulter matter case, you see interesting things. This is If I take the same simulation and I change dark matter nature and make it warm, you see I have a suppression of power. In this case, instead, I change the redshift organization, and so the level of smoothing, the filtering scale, which is related to the thermal history, changes. In this case, I have an increase of power. So the question that you can ask with such data in such simulation is the following. Am I living in a universe in which there is lambda CDM, or I'm living in a universe in which there is war dark matter, and the cutoff induced by war dark matter is cancelled by changing the realization history. And so this is a frontier of the field. I believe this is the high redshift. You want to constrain realization. I have slides later. And the statistical errors here are usually comparable or larger than non-systematic errors, because high redshift quasars are rarer. And so these data points that you see here are derived from, let's say, a set of 10 quasars or so. So if you improve this, you will improve the error, but you can disentangle between the models. If you move instead at smaller redshifts, you can think about feedback, right? For example, look at this case. This is a model in which you do have galactic feedback in the form of strong galactic winds, which are powered in several mechanisms. Romila has also worked on this, momentum-driven, energy-driven. And you see that if you have such a wind model, you have a boost of power at the level of 10, 15% at this case. I remind you the statistical error bars from both at this case is probably below the 1%. So maybe these models can be constrained. Of course, they very much depend on your actual physics of the aerodynamical simulation, but you do have, this also. It's not an overall amplitude. It's really a kind of, trend with wave numbers. So this S13 is a model in which galactic winds are present with a framework developed by Pukvine and Springle, always SPH code. Okay. So what is the primary reason for this? Well, you have two effects. You have the dynamical state of the gas that changes because of the wind, but also the gas is heated up, so the thermal state changes, and this is reflected by this change. And also, of course, the metal enrichment will change. So depending on the data set, you can ask different questions. Depending on the redshift, you can ask other questions. Okay? But data and simulations are there. Anyway, let's go to dark matter. So one simple case is a thermal dark matter candidate. In this case, you have a free streaming scale below which, basically, the thermal velocity of your dark matter sets this free streaming scale, and below these scales you don't have structure. And so in the simplest case, if you ask all this dark matter to be in this form, the only free parameter, let's say, becomes, well, omega dark matter and this mass of the war dark matter. The most massive you are, the closer you will be to lambda cold dark matter. And so here there are two cosmic web evolutions, from redshift 0 up to redshift 5, cold dark matter and war dark matter. Just to see by eye the fact that in war dark matter case the structure is smoother, there is less substructure. The point that I want to make is that if you take the circle about the beam of this beamer, right, this green dot here, these two will be the same, smoothed on these scales, but if you go to these scales, these two are not. So going to higher redshift, you'll be closer to the linear regime, and you can really probe the different dark matter nature better, right? Because nonlinearities more or less, let's say, tend to cancel primordial information, tend to evolve similarly in these two different scenarios. And that's what we did. Okay, we tried to look at this smoothing induced by the war dark matter structure, which is shown by these two lines, for example, here as a function of redshift. This is, if you wish, is the position below which you start to erase structure, and compare this cold dark matter or war dark matter fundamental physical quantities with the smoothing induced by astrophysics. There are three smoothings here, but two of them are more important. There is the thermal, 1D is the thermal broadening of the lines. The gas is thermally broadened, right? So in 1D you have these lines are smoothed by the thermal, by the temperature, right, of your gas. And then you have the gene smoothing, which is due to the gas pressure, which is 3D. But more importantly, you have the filtering scale, which is related to the gene smoothing, which depends on all the previous thermal history. If you change the realization, you will change the filtering scale. So here there is two important points to make. One, these astrophysical scales smoothing scale are larger than the dark matter cutoff, first of all. But second of all, most importantly, this is flat while these are not. So we can really single out this effect and get it out, having marginalized over this, because we have a wide redshift range of data, and we can probe the evolution of the flux power of this wide redshift range. That's the thing that helps us a lot in getting reasonable numbers, okay, reasonable and sensible numbers. 6 years ago, the status was this, and I want to show this because pretty much we are on the same situation now, even though we changed many, many things. So this is the flux power in a dimensional units scale green and red are two different scenarios with lambda cold dark matter and warm dark matter. This is SDSS 3, so it's not Bose, and this is the Mike and Iris. So you see that the redshift range spanned by this statistical estimate, right, of this cosmic Webb flux power is from redshift 2.2 up to redshift 5.4. Cosmic scales is about 0.5 up to 50 comoving megaparsec average. So it's pretty clear that these data points here are kind of important, right, because you start to fall short. But even if you didn't have this, also this one are quite important. Okay? This one, you start to have the hint of the cutoff induced by warm dark matter also a bit before. And since the error bars here are much smaller, if you neglect this and use only this, you will lower this by, at the level, you will go to 2.5 kV. You will not go to 0, okay? Zero constraining power. So both data are important in this respect. And both data are being used to do this. At that time, 6 years ago, we had a little, if any, exploration of the gene smoothing induced by, by change ionization. We also have just 2 data sets, and we improved the simulation side mainly rather than the data. And one improvement is given by this intermediate medium resolution data set here, which is called XQ100. And this is the likelihood, the posterior of 1 over m. I remind you, m infinite means lambda CDM. And so it means that 0 is the lambda CDM case. And you see the likelihood, look just at the continuous line for this set only of medium resolution data is quite broad. So warm dark matter is allowed here. But then if you take the high resolution data, you get squeezed in this part of the parameter space. And if you combine them, you gain also an extra bit, and you are down here. So this will be the 2 sigma upper limit, okay? Over the mass is 1 over 0.2, so it will be 5 kV in this case. So why is that you gain a lot by combining this? Why is that? The reason is that you get a better handle on the thermal state evolution of your mean temperature of the gas. So this is the measurements of the mean temperature evolution as a function of redshift. Also before there was a talk in cosmology in which they use this data to constrain dark photons in the universe. So the amount of energy injected in the intergalactic medium at this redshift is pretty much constrained by observation. And so if you ask yourself, okay, I have this high redshift data set, I have this low redshift data set, I can analyze independently, but I can also analyze them at the same time. And if I assume that this temperature density relationship and this temperature evolution is a smooth function, which is reasonable, then okay, the two will gain. You get a lever arm on this evolution, and you can get a type constraint. So when sometimes you see type numbers like 5 kV, these are mainly driven by priors on thermal history. Thermal history is the main nuisance now, and it's really important in going from 3 to 5. If you relax the prior, you will get something weaker. Let me skip this, but let me show you this, which is not my work. It's a work by Elisa Boera and George Becker. And so what they did, I think, is really nice. They focus in particular on the redshift ionization by using high redshift quasars. And so what they get is this green posterior on the redshift of ionization. And the nice thing, I believe, is that the error bar on this is at the same level of Planck. Completely different physics, completely different observable, and you get something very similar. If you combine them, you also, yes?
Is this assuming an instantaneous?
This is instantaneous. This is instantaneous, yes. Okay. And here they have marginalized over 2 astrophysical nuisances, which is the temperature after ionization and the slope of the radiation, how do you call it? The slope of the Heisenberg, exactly. But this is based on just 15 quasar spectra, and you see the error bars are similar to Planck, and I believe that you can really make progress on this. What do they use in this? They use the flux power spectrum. I use it for warm dark matter. They use it for ionization, and I think it's really improving, and it can be improved. So what could be the problems here? The problems are really summarized in this plot here. There is no consensus model on realization. It's still, we make progress, but it's a gray area. And so there is a claim by Kulkarni et al. That there are some islands of neutral hydrogen that are surviving at redshift 5.5. Okay, these islands of neutral hydrogen are big, so typically my simulation will not have this. Some box size that I'm dealing with are very small, so we don't have these things encoded in our framework. Maybe this thing can spoil us our constraints, can change the picture dramatically. And why is that people look at these models of ionization? Well, the reason is that you have things like this in the universe. Okay? These are two quasars, more or less the same redshift, one in one direction, one in the other. And in one case, you see you have a totally absorbed Gunn-Peterson trough. And you see here you should go to Lyman beta to find little transmission. In the other case, you have spike transmission spike. So why is the universe so, let's say, diverse? And well, one explanation might be this one, right? In one case, you're piercing the universe through this line. Okay, so maybe you will get that absorption trough, but in the other case, you'll be piercing through this line here, and then maybe you have transmission. One possibility. And this also goes back to if you want to, let's say, interpret one of the simplest quantities you might think of, the evolution of the mean flux as a function of redshift. These are the data, the measurements, and you have here extra scatter and also stiffness. Okay, of course, if you're approaching ionization, so you get neutral and neutral and neutral, the mean flux will become larger, of course, and so you will end up in this with the data in this part of the parameter space, and no models, the models that assume uniform UV background, uniform temperature, or let's say not patchy ionization, but uniform ionization tend to lie in this range here. Okay, so they do not explain this data. So there is extra physics there, and people are still investigating. There is this nice plot in on orbital paper in which there are two ingredients that you need to encode in your physical model. One is UVB fluctuation. Typically, we do this. We have this in our modeling. It's basically the fact that you have decrease opacity in overdense region, okay, and increase of opacity in underdense region. These are typically from rare sources like quasars. And also you have temperature fluctuation. This we don't. This we don't have, and people are folded in these. Few groups have them. I don't. When I quoted the results that I showed before, we don't have these temperature fluctuations. And typically, these temperature fluctuations are due to this fact that the ionization is not homogeneous. Some regions will, let's say, ionize first, and then by later we'll have cool down. And so typically, these temperature fluctuations are instead correlated with densities. And so you want to have this physics right, and you want to see whether these quantities here will impact on this flux power spectrum, okay, measurement, and will impact the cosmic wave properties. So one possible way, which is a nice way of also, make the crosstalk between emission and absorption, is to look at along the direction of this Gunn-Peterson trough, which is very, absorbed, and you look at Lyman alpha emitters around this. This is a work by George Becker. And if you look at the abundance of Lyman alpha emitters around this line of sight, which is this cross here in the very center, there is a depletion of Lyman alpha emitters. And this make a kind of strong or maybe weak case, I don't know, it depends on you, for the case that the fact this absorption trough is piercing through, an underdense region. So if it is underdense, it's not due to temperature fluctuations. It's due maybe to UVB fluctuation of this island of neutral hydrogen. And this is obtained by looking at Lyman alpha emitters around a very absorbed line of sight, exactly the one that I showed before. This is not my word, but this is the frontier in the field, getting the physics right at this high redshift. These are very constrained data points, right? At redshift 5.4, you will be probing dark matter much better than at redshift 5. So these are UVB fluctuations by Honor et al. You see the effect in terms of flux power. This we have in our Monte Carlo Markov chain. And this is the temperature fluctuations. And the point I want to make here is that they don't seem, at least in this incarnation, to produce a reasonable effect on the flux power at small scales. People like working on world dark matter, what would they like? They would like to have something here that increase the power in order to counteract the suppression of power induced by world dark matter. So their world dark matter model could survive. This temperature fluctuation, if the physics is correct by this group of people, will not help in this respect to weaken, to make these bounds weaker. And this is again reiteration on the same side, along the same line by Pukman et al. This patch ionization, you see, will boost power at large scales, but will leave pretty much unaffected the small scale power spectrum here. Okay? So I think it's interesting. So how am I doing with time? 10 minutes or so. Fuzzy dark matter is very popular. The physics is simple. There is lots of work done. There is this nice paper by Lam that you are aware of. There is these people like David Marsh who has been working on fuzzy dark matter for 20 years now is very nice. So the physics is simple. I'm sure you've been exposed to fuzzy dark matter being here. And the same story holds true for fuzzy dark matter for Lyman alpha forest. If you have a candidate, let's say, of 10 to the minus 21, which is kind of, at the upper end of that, the numbers that people would like in order to solve the crisis of Lyman cold dark matter, you start to fall short at high redshift. And it means that the Lyman alpha forest wants values of this which are larger than this one, a few times 10 to the minus 21. Let me skip this. I can also skip this. Let me go to emission, okay, and then I'll conclude. In the past, we look at this with Paco, right, when he was in Trieste, and we look at the 21 centimeter, well, in this case, with the H1 power spectrum, and we had several sets of simulation at different box sizes, 15, 30, 60 megaparsec, and this is with wings, without wings. We look at the scale dependence of this bias of the H1, and so we wonder why is that you have such scale dependence, why in some cases you have flatter, but the scale dependence starts here is due to the nonlinearity in the bias, is it due to something else, and we try to look at these things by populating halos with some recipe, right? In the spirit, in a way, of the halo model. So we start to explore this somewhat systematically, especially to see whether feedback or galactic astrophysics could destroy, could spoil the properties of this power spectrum. So at that time, there were a few questions, however, that were important for us, even now, to some extent. And the first one is, can you use this observable to improve the neutrino mass limits? And so what we did here is we considered the bias of the H1 in 3 different universes in which the mass of the neutrinos increases from 0 to 0.6, and the bias of H1 increases. And the reason is simple. You want, in this exercise, to have the total omega H1 fixed. So in a universe in which neutrinos are massive, you start neutrino free streaming tend to change the mass function to deplete the number density of, let's say, halos below a given mass, okay? And so you tend to put slightly more halos in this universe, massive neutrino cosmology simulations. You tend to put slightly more neutral hydrogen in this case, while in lambda cold dark matter you can throw neutral hydrogen, populate your halos with neutral hydrogen down to small scales, okay, down to small masses. And of course, if you put more, these halos will be more biased. That's why you have the boost. Okay. But then if you look at the real observable, which is the 21 centimeter, in front of it there is this brightness temperature, which depends also on the bias and omega H1, okay? And so you will have a kind of opposite trend. So what did we have here at the end? We have a limit which was not very interesting in a way. It was about 30 millielectron volt, was not very constraining compared to limits suggested by other probes like DESI or other spectroscopic survey. And the claim that we made was that if you also try to kind of explore different way of populating these halos that should mimic radiative transfer post-processing, right, you end up pretty much on the same ballpark of limits, 30 millielectron volt. And you gain a lot only when you combine to survey like SpectroZ is Euclid, basically, Euclid-like. Another thing that I think is particularly nice and people maybe are not very aware of is that you can use intensity mapping to do baryonic acoustic oscillation studies, right? You will think that this is not possible because intrinsically intensity mapping has very poor angular resolution. That's true. In this case, what you see the baryonic acoustic oscillation in the correlation function, 21 centimeter. Here is the linear case. Here is what you get smoothed by nonlinearities. And then you can, okay, on top of this, you have an extra smoothing due to the instrument, 5, 10, 15 H over megaparsec, and you see that the baryonic acoustic oscillation peak disappears. That's reasonable. It's reasonable, and it happens for megaparsec corresponding to angular scales of SK1 mid. So if you look just at this, you'll say, I cannot do any baryonic acoustic oscillation with this. But in reality, we looked into this a bit more carefully, and it's true that your angular resolution is poor, but your radial resolution is very good, right? Is a frequency intrinsically spectroscopic signal, and so you have really, really huge resolution along the line of sight. And if you look at the 1D power, it's true that if you increase your angular resolution, this gets lower and lower, reasonably. That makes sense. But if you divide it by a power without baryonic acoustic oscillation, the oscillations are kind of still large. And so we coded this up, also trying to do things a bit more, let's say, closer to experiments, also by putting the foreground, extract the foreground with a very simple principal component analysis. We took the mask, and we said, okay, are we able to get the position of the baryonic acoustic oscillation also in the presence of noise and foregrounds, and with and without the mask. And of course, depending on the redshift, the error on the position of the peak, one is the real position, gets degraded up to a factor of 2, but this seems, according to this, of course, very preliminary, but still in a way sophisticated, I would say, study, baryonic acoustic oscillation could be performed. And let me stress that this will go up to 2.5. Okay, so it's relatively high redshift, which is something that we will have very little access to geometry of the universe at this redshift. Incidentally, it's the same redshift of the Lyman force baryonic acoustic oscillation. So we might want to see whether the two are in agreement, right? So small scales are also very important. If you look, for example, at the zoom in these 10 to the 13 halos, this is the H1 profiles at small scales. You see this huge amount of scatter. Of course, in this TNG illustrated simulation, you have many halos, so you can really look at this envelope of profiles. And this profile changes because of physics for less massive halos. This is 10 to the 9, looks a bit different compared to this case. Of course, as you know, people like you that work on these things, they know that this is an important ingredient in halo models. You need to specify these things, halo models, in the halo models. You need to specify the H1 profile, and it's really different depending on this. So you want to fold this extra information into your halo model prediction and see whether or not these things are important, for example, for redshift space distortion, finger of God effects, and things like that. It propagates from small scales to large scales easily. Let me skip this. One other thing that we are doing with Marta Spinelli and Gabriela De Lucia semi-analytical galaxy formation models is to look at whether we can study a bit more carefully this fundamental relationship of H1 as a function of the dark matter halo in terms of galaxy properties. Okay? So for example, what you see here is basically something very simple. We did this exercise, we took the millennium simulation, and we ran on top of this semi-analytical galaxy formation models, which follow star formation, cooling of the gas, feedback processes, to a quite a degree, is tailored to reproduce observations, of course. And we try to break up also, as a function of redshift, the color coding here is redshift, but we try to see whether this H1 resides mainly in centrals or satellite galaxies. That's one thing that we can ask. The other thing that we can ask is whether this curve here, this divided by H1, has any dependence on the formation redshift of the halos themselves, which is, in a way, goes in the direction of assembly bias of these halos. Why do we want to ask this question? Because if you think about it, it's quite possible that this intensity mapping exercise will be done and will be performed on top of cross correlations, right, rather than actual flat auto power spectrum. And in that case, might be interesting to say, okay, I have this volume in which I have my intensity mapping information. I want to cross correlate this with a population of very active galaxies, very star forming. I want to cross correlate this with a population of galaxies which are not star forming, and see what I can learn in terms of the signal itself by doing this exercise. I want to specify the role of assembly history over time and things like that. I think yes, these are my conclusions. So I gave you, I made a fast path through to having a common denominator neutral hydrogen and highlighting some absorption lines properties, right, and emission lines. And we are probing the universe. We are probing the universe using two different tracers, right, two different observables, but it's the same element. It's neutral hydrogen, atomic hydrogen throughout cosmic time, and especially in the post-ionization year. So it's an important tracer, and you can do it to perform quantitative cosmological studies. For the absorption lines, we are already doing this. For intensity mapping, we can do this in the future. And it's very complementary to other probes, right? CMD probes the large scales, weak lensing probes somewhat intermediate scales, galaxy clustering still large scale, I would say. This is down to small scales. So what do we have from the Lyman alpha forest? No support for neutrinos masses larger than 0, no evidence. We know that there should be mass larger than 0, but so far we don't have a detection. Or no support for non-cold dark matter. What does it mean? It means that there could be dark matter, but is basically mass is so large that in terms of forest properties will be very much similar in terms of structure formation to the cold dark matter particle. This is the main conclusion. The new frontier for the forest, I believe, is the high redshift, close to realization, and also at the same time try to analyze 3D and 1D flux power, self-consistent, which has not been done for obvious reason. Theoretically, it's very difficult to have these huge volumes for 3D and high resolution for 1D. On top of that, I believe another interesting avenue is to explore higher order statistics, bispectrum or other quantities you might think of. Then I believe that the progress in 21 centimeter maps is to use n-body simulation with inputs from very accurate, let's say, possibly, full of physics, hydrodynamical simulation, which incorporate the relevant physical aspects. And even in that case, you might wonder, okay, then maybe it's only large scale, maybe I don't need the small scale, I don't want to look at them, right? Sometimes it's better not even to look at small scales because maybe they don't add anything. They add just noise, or they can constrain parameters that are probably just the nuisance parameters. But however, even in this case, and I believe that Paco showed this quite well in the last few years, it's important to model to some extent also the small scales. Getting the H1 profile right will affect the fingers of Groth and fingers of other redshift space distortion that propagate out to the larger scales. Observationally, in this respect, I believe that in both aspects, I believe that cross-correlation studies, for example, dumb Lyman analysis system with H1 forest absorbers, can constrain the model further, and also for intensity mapping, you can cross-correlate intensity mapping with galaxy properties, and I believe progress can be made also in this respect. And I think I can end here. Thank you.
Questions?
I'm curious, so a lot of times we use these sort of characteristic statistics like the flux power spectrum, flux PDFs, column density distributions. Do you think there's also room for higher order statistics in this picture, like especially at high redshift? I mean, what in terms of machine learning, which is something a lot of people here are interested in? How do you see this developing?
I think so. In the past, I also worked quite a bit on the flux PDF, and it's a surprise, or maybe not surprisingly, a very difficult statistics to get right. So you might ask myself the following question: why should we believe your flux power spectral results if you cannot model properly the flux PDF, right? Maybe there is extra physics that we're missing. Well, we have some ideas. Maybe in the flux PDF, for example, there are some systematic effects like continuum fitting that we don't marginalize over properly, and these affect much more the flux PDF rather than the flux power. But to answer your question, yes, I think that progress should be done, especially in the context of trying to fit all the statistics of one in a comprehensive framework like 3D, 1D flux power, which has not been done. Look at the bispectrum could be promising. Also, maybe if you want to look also at non-Gaussianities, right? These things, or maybe it will add extra constraining power on the thermal history. And regarding machine learning, I think again there are one thing that I always ask myself is typically in this BOSS survey you have rather poor resolution. The line of sight mean separation is maybe tens of megaparsec. And so from this, maybe you can do tomographic reconstruction studies of by interpolating between this line of sight information of the dark matter field and things like that. And maybe machine learning can help in this respect. I haven't worked myself on this thing. The other promising path is that at this point, we have something like 20 parameters in the MCMC. So scanning this parameter space efficiently is sometimes tricky. Okay, even if our likelihood is not particularly complex, you have 20 parameters. To get convergence is sometimes very difficult. You need to run for a week. Okay? And so if you have some clever ideas on how to span this parameter space, or maybe there are people like working on emulators like Irania Paris, Simon Bird, they also can tell you in which direction maybe preferentially you need to throw your hydrodynamical simulation in order to improve some, the posteriors. And so in this respect also there is, I think, a scope for improvement. Yeah.
So
So if someone asks you what is the number that we should set for order matter, is it still 3.3?
No, the number, in my opinion, 3.3, 3.5 is conservative and correct. 5, which I also wrote in a paper, 5.2 or 5 point something, that is, let's say, a bit less conservative, okay, a bit. There is also papers, there is a paper recently by people in Paris, they claim 10 keV, okay? 10 keV is absolutely wrong, okay? And so, yeah, 10 keV is really too much, and you can. I have to say there are also people, this group of people working on sterile neutrinos, their approach is to study this data in a frequentist framework. So what they say is basically, okay, we believe in the sterile neutrinos with this mass, and then what is the thermal history that you get in order to have this candidate accommodated? And the thermal history that they get, they are on the cold side. And so, and they claim that even 2 kV could be correct. And I believe that, again, is a far stretch. 2 kV is a bit too low.
Go ahead, please.
I wonder about how well the Halo model framework works for modeling H1 for several reasons. In the inside of the halo, it seems like H1 distribution is fairly inhomogeneous, and therefore you get fairly large scatter in any given halo. I also wonder about how much H1 is out there outside of the halo, and also to what extent we can believe in the current simulations for producing H1 in filaments. And there is also a recent paper about the cosmic fog in things like cosmic sheets, which occurs due to thermal instabilities. So these are sort of new phenomena that has not been captured in.
But are you worried more about emission processes rather than absorptions, right? Or both?
I'm sort of asking generally about how accurately you are modeling H1 and how well we can use a halo model to actually capture all of these sort of sufficiently complicated physics.
So these profiles, this envelope of profiles have been obtained by looking at many halos in the illustrious TNG simulation, the latest version, right? Which is supposed to be one of the best, if not the best one, in reproducing many physical properties of the galaxies. And so you might wonder, okay, if I implement the mean relation in my halo model, then I don't consider the scatter, which can play a role. And maybe, yes, you can improve on this. Or you might wonder, maybe the physics is not correct. If I did have some different feedback scheme, this curve would have changed. Maybe this would have been steeper and this would have been shallower. And the halo model at least has the flexibility to kind of fold this thing in a simple way. At least it's something that you can use, can be reproducible. But I agree with you, there are some assumptions getting this curve. And about the quantity of H1 outside the halos, we looked into this in the past. And I believe that depends on the redshift, of course. At redshift 5 is something like 10% or less. At redshift 3 is probably 1% or less. So, but again, when we derived these quantities, we had, pretty simple setup of simulation with some feedback, of course, but some specific models. Okay, so it's not, by far, it's not comprehensive analysis of this. With maybe Paco and Shai will do this with machine learning by using, I don't know, 40 or 50 different feedback schemes, hopefully, and then we can tell us what is, how these uncertainties will propagate on the signal. There's also to say that the intensity mapping, you have the thermal noise of the instrument at small scale, right, which erase power. So in principle, even to some extent you want the redshift distortion pattern correct, small scales are not that important for intensity mapping.
My question was sort of a variant of his. It was sort of the Pandora box of looking inside the halos and looking at the satellites, which is, I would expect there to be some radial dependence on the satellites close to the center and far away, but if you don't care about those scales, maybe.
Well, in this case, for these millennium simulations, apparently you do. These are relatively high resolution simulations, and so you can really follow the evolutionary, you track the merging history.
Blue and red galaxies, they're more red ones inside.
Yeah, I have a similar plot with the radial dependence. Let me see, maybe we haven't looked at this carefully. But I have a similar plot in star formation, for example. How much H1 is in blue and red galaxy. I have a similar plot. We haven't looked at the radial dependence of this. Maybe you looked at this, no, because you didn't break between central and satellite
It's
galaxy.
definitely small scale at that point.
Yeah.
The homogeneities may be already up. So.
It could be interesting. I agree. Could be very, very important. I don't have an answer, but that's another thing to look at. Absolutely. Yeah.
Most questions? No, we can. Thank you.
Thank you.